Thanks again to Justin and Scott. This is my shameless plug for an event we're going to have at the end of May. Some of you might have heard of it. We still have registration open. It's Haystack 2015, a DH conference at Michigan State. Everybody who comes gets one of these cool mission patches, a real live mission patch that you can put on your jacket. So if for no other reason, that's why you should come. Today I'm going to talk a little bit about some work that we've done in a group called Computational Rhetorics Research Group out of the Wide Research Center at Michigan State. And this is my take on some of the work of a lot of people. And so I will occasionally use that word we, and I mean all of the folks at the Research Center, including some undergraduate students and graduate students, and I'll name them as well. But if I say I, it's usually the things I want you to blame me for. And if I say we, it's the things that they deserve probably more credit for than I do. So I'm going to start and show you what we made, and then I'll kind of come back here. So I'll see if this works for us. So this is a little app that runs in the browser called the Faciloscope. It's made to help people who work in science centers and museums who do something called facilitation, which is to informal learning what pedagogy is to formal learning. To monitor and moderate online discussions of various sorts in social media, on blogs, in various places they might occur. And they had a common problem, which is they have a lot of this activity and they want to know when is the right moment to intervene. We also want to know this as teachers, right? Sometimes you want to hang back and let them do their thing, and sometimes you want to get in there and give a nudge. And that can be very difficult, particularly around scientific topics on the web that also attract a variety of other kinds of opinion. If you think about climate change, for example, and if you may have heard last year, about 18 months ago, Popular Science decided to shut down their discussion forums altogether because there was so much trolling going on and so much political wrangling that the science wasn't getting discussed. So this is the kind of scenario that our museum folks found themselves in. Based on some work that Jeff Grable and a team of intrepid students had done prior to this, we had a fairly good idea of what facilitation moves were important to these museum folks and what could cause downstream more helpful conversation. And they had actually done this work outside of digital spaces as well as in digital spaces. And so we set about trying to figure out if we could speed that process up, because when Jeff's team did it, they needed a team of trained rhetoricians and a lot of time and about $500,000 from the IMLS to get it done. That feedback loop was much too long for it to be useful in the actual context of use. And so that was the scenario. So what we're going to see is I've pasted a discussion thread from the wild. This is from discover.com, Discover Magazine, on climate change. I've just stripped most of the text out of there. These are a conversation that happened underneath a particular story, right, in Discover. And I'm going to hit the Analyze button, and the Faciloscope is going to show us what's going on in that thread. And what it's actually looking for are 3 signature facilitation moves. So what it's done is it's broken down every sentence, and it's tagged those sentences or classified them into 3 key moves. Staging, which you can see is the most, that's the green part of the donut. Staging moves are generally not terribly interactive. They're just people sort of either setting up a conversation or just stating a claim. The other 2 moves are much more signature of this kind of facilitation activity, whether it's happening because a formal moderator is doing it or the participants themselves, invoking and inviting. And you can see that there's a little bit of the purple there. That's inviting. That's when somebody asks someone for their opinion, asks a question. And invoking is a narrow slice. This is the percentage of the total. When we go down here, we have a couple of other ways to see that. The move pattern shows those same activities. So now left to right, you're seeing where the concentration of those moves happen. So what we would see in this thread over time is that people aren't generally talking to one another very much. They're just sort of going on about their own positions, except right there at the end. And if we actually zoomed in close to the end, and I could show you the natural language text here, right? So we don't take that away. If we looked at this more closely, we would see that there's a fair amount of trolling going on there. So it's not even positive activity. It's they're calling each other out, but they're kind of doing it in a mean way. So that's the oscilloscope, and I'm going to talk a little bit more about that in the context of the talk, but I wanted to give you a sense of what we've been doing when I say teaching machines rhetoric. So feel free to ask more questions. Sadly, we won't get to play with the toys very long. When we talk about how people learn a particular set of rhetorical moves, you've heard me use that word a couple of times. I kind of mean it in the Swales sense, but I'm also being a little bit more general, talking a little bit about how folks get used to making moves that others recognize as valid moves, right? So it does connect with this phrase, available means. One of the things that means are available for is reuse. It may not be reiteration, but these are how these kinds of rhetorical gestures, as we heard Byron talking about, get picked up by others. In our particular case, we were looking at, and we have been looking at, how do discussions that are generally about science, how do they move forward with the idea that other people are signaling to one another not only what they're talking about, but that they're doing it in a way that resolves to talking about science. We started looking at that information by looking at how scientists do that, right? When scientists in scientific journals are talking to other scientists, are there signals for that? And there, of course, are. One of the more powerful ones is hedging your claims based on the strength of your evidence. Something that politicians don't do very much, but it's something that scientists do constantly. And they do it not only because it matters to their argument, but because it tells the other scientists that, hey, I'm a scientist doing science like you, so please accept this as a scientific statement. What that means is that what gets repeated is a really interesting idea. So part of what I'm going to talk about, and I think some of the other panelists are going to give us some discussions about, are the limitations of algorithms for learning based on repetition, or what we might think of in rhetorical terms as imitatio. Learning to see a consistent pattern based on something that is repeated. And the question is, well, what gets repeated in rhetorical learning? In the title of my talk, I mentioned the prohymnasmata, which is a sequences of rhetorical activities, of rhetorical exercises, really. It's been interpreted over the years in various ways, but if you look at how it's meant to provide scaffolding for a learner, early on, they are repeating exact words and phrases, often the words and phrases of other well-known rhetors. But over time, what happens is that the learner begins to abstract those a bit. They get unique situations, and they're asked to do the same kind of moves, but not in the same words. And so these moves become the things that get repeated. But when we start talking about how we find those, particularly when computers are involved, it becomes really tricky. So let me show you an example of what I'm talking about. So if we think about reuse simply as repetition of words, and this is something that a lot of algorithms take a lot of heat for, they're bad at it. So this is a little tool that's made by this Advanced Marketing Institute online. And it's supposed to tell you how to write an emotionally effective headline for your page. So I picked one off of Upworthy. Some of you might know Upworthy. They actually use human power to decide which headlines work best by something called A/B testing. They put a couple of headlines out there at a time. The one that gets the most clicks starts to win, and then the other one dies off. They're famous for these kind of clickbait headlines like the one that I grabbed here. His classmates thought making fun of him made perfect sense, but then a senseless thing happened. Right? That's awesome. So the dictionary-based algorithm that is in this particular trinket tests this, and you can see it comes back with 0.0%, 0.0% emotional content, right? Now, I don't agree with that. You probably don't agree with that. It's not seeing a pathos appeal, right? So why? Let's think about why. Well, what is it looking for? what is it? It needs to see something repeated that it has seen before in order to recognize that. So it's probably doing something like this. And I say probably because I haven't looked at the source code, but it's pretty common kind of trick. So first what they're going to do is they're going to strip away the words that they think, by definition, because the kind of words they are, don't carry emotional content. They're not in the emotional dictionary, literally. And then it's going to reduce that string to a set of tokens, individual tokens. And then it's going to compare the emotional value of each of those tokens. So that's what it's seeing is down there, the tokens, classmate, think, make, fun. And there may be one word in there, fun, that probably should have tripped the emotional meter, but for whatever reason, it did not. So if we're thinking about trying to help it find moves in a different way, and one of the things that we're trying to understand here is also how humans would do this. So clearly we see something that the computer doesn't. So how might we get around that? So Anthony Pare is talking a little bit about genre theory here in a way that we found particularly useful. And this is a notion that he talks about as even repeated instances of a genre are always custom. And that means that humans must be really, really good at detecting around the edges of a particular situation. They detect what's common, and then they zero in on what's novel, right? And this is what I found resonating so well before the break with Byron's talk, with just how little of that overall signal has to be new to be recognized by a human as, oh yeah, that's kind of interesting. That's something new. But in order for that to happen, it's usually surrounded by things that are not terribly new, where there are a lot of stable structures going on, all that signaling going on that says, hey, here's what's going to happen. We also had to think procedurally about how we process this information in order to turn a text into something that a computer can understand. A computer is not going to read a text except in a way that we give it to understand. And in that regard, we have a few choices about what kind of computational object a text can be. In the previous example I showed you, the engineers had decided that it would be a string of words, a string, right? But that's not the only choice. And we actually got to a different choice. And I'll talk to you a little bit about that in more detail in a minute. But here's how we got to that choice, by some theory that most of us in the room are familiar with, even if we haven't quite seen it this way. And that is, so what are people seeing and understanding? Probably not individual words measured by their semantic weight or by their emotional content, but rather we're stringing those words together, whether we're reading them on a page or hearing them, and we're making little structures out of them. We're creating something like a network, right? Or in our case, a graph. A network and a graph are synonymous in mathematics, and we can do some interesting math, that is some interesting computational work on graphs. So here's what that same string might look like as a graph. And that's not just a random string of dots. What I've done is I've done a little bit of a different parsing of the tokens. I've actually chosen to leave some words in that most folks would take out, because I suspect that they have a role to play, not in as tokens themselves, but in building little structures that help create an appeal to pathos. So reference to humans seem important, right? Even if they're pronouns. Also, those things like reversals, the but and the then. All those kinds of conditionals. So here, if you see the bold tokens in my sentence, they actually appear more than once. And the red tokens are stop words that in most schemes of natural language processing would get thrown out. And what we could start to see is a little network shape starts to form. Another question you might have is, how do we build this? This is just the words in order, right? So I'm making connections between words in the same way that a speaker or a writer does, by setting them next to one another. And that's the default connection. And where a word recurs, we don't necessarily make the chain longer. We make a new edge to that same word, so that we start to see how important or how central a particular token is in the overall network. And now you heard me start using some network metrics. So this is the world's briefest discussion of network analysis, or graph theory, really. Networks have physical properties that we can analyze differently than strings of text. On the left side, you see, for example, is a distribution curve that results from the network that is up there. And all we're doing there is counting the number of edges that each node is connected by. But we can also do something else about the structure of the overall network. And that's the adjacency matrix on the right. The ones and zeros tell me whether or not it shares an edge with any one other node. So from there, you can see the node in the middle position, which is very important. If that's your cable company, you don't want node D going out, right? Because everybody on either side of the network loses connection. You can see that that's the fourth line in the adjacency matrix. It's got all ones across the board. But if you look more carefully at that, something else happens. So look at that right-hand adjacency matrix for that network of tokens, and you start to see something that looks like a digital fingerprint. And it's a digital fingerprint that we could substitute out the semantic tokens and still retain the structure of. Especially for the high centrality content words, like classmate. It wouldn't have to be, we wouldn't need classmate, because classmate's not that important, it's not that central. The structure would stay the same. And so what we're seeing, we think, is something that looks a little bit more like a rhetorical move rather than a string of tokens. Now, in real life, networks are not that small and tidy. That's one of the chicken thread, a thread that has lasted about 8.5 years on this science blog. So, wow, it's a tidy idea to sort of model a small phrase. This is more like what we're thinking about when we're trying to understand the structure of a complex conversation about whether something is science or not. So we have to rely actually on the math to do that. So when we talk about computational rhetoric, this is really what we're talking about, applying some computational tools to understand what might be rhetorically interesting about a text, or in this case, a large selection of text. So you can see in this particular case, this is where we see the evidence for why hedging is important. We see the high centrality content word that tells us what this thread is about rising to the top. That's roughly what happens in something called topic modeling, which you might have heard. But if you look at what else is high centrality in this little table, the very next word is if. And then down below, we have can and will, these modals. Modals and conditionals near high centrality content words turn out to be really interesting because they are hedge moves. They indicate that people are treating the topic in ways that science treats those topics. So when we see that co-occurrence, it's a pretty stable indicator of when we're seeing scientists or scientific discourse or something like it. If we zoom in on that big hairball I showed you before, we can also see something fairly interesting, and those are cycles. People keep coming back to those tokens. When we say that a token is high centrality, that means that it occupies a place where, if you imagine these as walks, as conversations that actually go on in time, people come back to that word. They keep saying egg, 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 egg. Over 7 years, we don't see any conversation go very long without someone uttering the word egg. And the same is true of words like it. All right, so I got to cut to the chase. What we think we're doing here, I can't tell you if it's the same way that the humans are understanding the way we find moves like staging, which is similar to hedging in some ways, inviting or invoking. I can't tell you if the computer and the human are seeing the same thing. I can tell you that we can get the computer to agree with a human about the same rate as we can get another human to agree with the human. And we do that with supervised machine learning. We feed it enough examples, we see enough repetition, and it starts to see the pattern. I can talk a little bit more about that, but I want to close with a few. That's a terrible neologism. Automagogy, pedagogy for machines. What does that look like? We want to be really careful. So far, we are only building tools that work alongside humans. We aren't interested in building tools that replace humans in any way. We've worked with very, very narrow ways of doing this as a result. But I suspect that not everybody is interested in that. I think there are people, the tools that we've used are readily available. Other people can use them and other people can build them. And I would not be surprised if they're doing that without us knowing too much about it. So we should be mindful of what folks like Janet Atwill and Jasper Neal and Malia Powell talk about, which is that rhetorics, once revealed, tend to consolidate power in the hands of the powerful. When we black box the kind of rhetorical knowledge that's going on in these applications, we also ought to probably help people understand how the machine learned it to begin with. As I say, machines and humans may see those texts differently, but I would urge us not to get too caught up in that problem. It won't be that way for very long, or it won't matter, one or the other. Because if we agree at the end of the day, we can substitute one judgment for the other all too easily. And we're seeing that with machine scoring of student grading, for example. It won't be our decision to make once that decision is very reliable. And then finally, the high-speed securities trading issue. We're going to see some collapse in that industry. And if we're not careful, we may see some collapse in the kind of things that we used to think were the sole province of humans too. So we have to be mindful of how these machines are learning these things, and we have to get involved. So I'll stop there, and we'll hear more about it. Thank you.